Good morning. Am I audible? Hello. Good morning. Am I audible?
Yes, sir.
Okay. Okay. Yesterday, so we discussed how to insert at the front, how to insert after a node, and how to um, uh, insert at the front, and how to insert at between, and how to insert to a shorted list. So there's a few things what we understood yesterday to a given singly linked list, and then we were discussing the applications of the singly linked list, and one such application that we understood was using singly linked list you can go for performing the operations on the polynomials. So we just understood how to do the polynomial addition using the singly linked list. But only thing is here you have to create a node which has three fields, one for holding the coefficient, one for holding the exponent, and another for holding the address of the next node, that is link. Okay, so and then how to represent it also we understood. You can create a simple structure with the name polynode, and you can define the one integer variable for coefficient, another integer variable for exponent, and a self-referential links to the same node, so that is called as link. So star link is a pointer of type polynode itself. And then as an example we understood how a polynomial is represented using a singly linked list with three fields. Okay, so this is what, and after that we understood the rules of adding the polynomials. Okay, if the exponents of the terms are same, then we add the corresponding coefficients. So that is what is shown over here. So the exponent of this and the exponent here of a polynomial and b polynomial were same, and we have added the corresponding coefficients and we have written it, and this is my new resultant polynomial. And next, if the exponents are same, what we do, we increment a and b, both are incremented. Now a is pointing to this node, and b is pointing to this node. Again what we do, we go for comparing the exponents. So the exponent of a here is 8 and the exponent of b here is 10. So now the exponent of a is lesser than the exponent of b. So always choose the node which has if they are not same, if the exponents are not same, go for choosing the exponent which is bigger. Okay, so now what I do, so since the exponent of b is bigger, so in the next term in my resultant polynomial is the term which is there in which has the highest exponent, so that is -3 and 10. I'm writing it now. What you have to do is you should increment only b. So a is not incremented, a still points here itself, so b is incremented. Okay, so next what I'm doing, so I'm again comparing the exponent of a with the exponent of b. So exponent of a is bigger now, higher. So now the next term in the resultant polynomial is 2, 8. Okay, and a is incremented. So this process we repeat until we reach the end of the polynomial. Okay, and the implementation of the same also you understood. So this was the corresponding implementation for it. Okay, and when you compare, so three things you are checking here. One is equal to, another one is exponent of polynomial a is lesser than the exponent of polynomial b, another one is exponent of polynomial a is greater than the exponent of the polynomial b. So whenever it is equal, what compare returns is 0. Whenever the exponent of polynomial a is lesser than the exponent of polynomial b, what compare returns is -1. If the first term is lesser than the second term, it always returns -1. And similarly whenever the first term is bigger than the second term, it always returns a positive number. Okay, 1. Now based on that, so we have written this. We are comparing the exponents of a and b. So if it is equal to -1, what does it mean? The exponent of a is lesser. So that time to the resultant polynomial, you got to attach the coefficient of b, exponent of b, to the rear end of the resultant polynomial, and then increment only b. So b is made to point to the next node. So b is made to point to the next node, and next is case 0. So that means if they both the exponents are same, what we do? So we find the sum, we add the corresponding coefficients of a and b, and then we attach the sum and anyone's exponent, because exponents are same. A's exponent is also same, b's exponent is also same. Now you can go for attaching the sum. This is your new coefficient, and you can pick either from a's exponent or b's exponent, and you add it to the rear end and go for incrementing both. A is also made to point to the next node, and b is also made to point to the next node. So if it is case 1, what does it mean? The exponent of a is bigger than the exponent of b. Then you attach the a's coefficient and a's exponent to the rear end of the resultant polynomial and go for incrementing only a. Okay, and after that, okay, so till you reach the end of your a polynomial. So if there are some terms remaining still in the a polynomial, so run a for loop and just attach its coefficient and exponent to the rear end of the resultant polynomial, and the same thing has to be done for the b polynomial also. And finally terminate the last node link field of the resultant polynomial to null. Okay, this is what we people do. I hope this is clear. So this I told yesterday also, but I am refreshing it again. Hope you people understood with this. Hello.
Yes, sir.
Okay. Now as a circular list, so I think yeah, we got to discuss from here. So that was just a recap of because, so if you know this, okay, so then you can easily understand this. Okay, so now representing, so here we didn't use the concept of circular single linked list. What we used was only a single linked list concept we used. So now how do we represent polynomials as a circular linked list? Okay, now when I say a circular linked list, it is something like this. Okay, I have 3 fields again here. Okay, one is for the coefficient, exponent, and the next field. Now instead of storing null in the link field of the last node, what we do now, we store the address of the first node such that we can reach back to the first node. Okay, now this is 0 polynomial. When there is no there are no terms in your polynomial, so this is how the status of a circular single linked list will look like. And this field, okay, exponent field, so we make it as -1 because 0 polynomial, or this we call it as an header node also, we make it as -1 initially. Next, so if it is not a 0 polynomial, say I have a polynomial something like this, how do we represent it? So this is the header node, okay, and a is pointing to this node, and this I intentionally make it as -1, and in this field I store the address of the next node. So in this next node, so it has the coefficient of the first term of my polynomial, that is 3, and it has the exponent of my first term in the polynomial, that is 14, and this field is holding the address of the next node. So the next node, when I look, so it has the coefficient 2, and then the exponent, its exponent 8, and this field is storing the address of the next node, and this is 1, the coefficient, and there is no exponent here. Okay, so it is something like x to the power 0. X to the power 0 is nothing but what? 1. Now I am writing the exponent as 0, and in this field, in the previous example, what we were doing, we used to store null here. Now instead of storing null, now I am just storing the address of the first node, this node here. Okay, so that means even when I'm at the last node, it's possible for me to get into the first node again. Okay, so this is. This is how a polynomial can be represented using a circular singly linked list with header node. So this is called as an header node. The one which you're seeing in yellow color is the header node, because my actual polynomial starts from here. Just to link it back, I'm just taking an header node. So now implementation of the same. So implementation of the adding two polynomials just using a singly linked list, you understood. Similarly, implementation of the adding two polynomials using circular linked list. Okay, circular singly linked list. You can just observe here. So poly pointer. Now I'm calling it as CP add, circular polynomial add. Okay, because what we are defining now is the circular polynomial, and then two pointers I'm passing. So poly pointer A and poly pointer B. So A is pointing to the first polynomial and B is pointing to the second polynomial, and inside this function I've taken it as start A, D and last D. So start A, I make this pointer point to the first node or the header node of the A polynomial. Okay, and I have other variables also, integer variable sum, and done is equal to false. Okay, because I'll be running the do while loop, and to just terminate this do while loop I'm taking this done is equal to false. Even in the lab programs we used to initialize done is equal to 0. Okay, not of 0 used to be 1, and it used to display the menu option again for you. And when I don't want to continue with the execution, I used to select the option 4, and when it goes to option 4, done used to become 1 and not of 1 used to become 0, and the program used to get terminated. So similarly, so I have taken done is equal to false, or else you can say done is equal to 0 also, because false and 0 means the same when I consider them as the boolean values. Next, what I'm doing, start A is equal to A. Okay, so this is what start A, I made it as a poly pointer. Now start A, when I say start A is equal to A, what is happening here? Can anyone tell? Now start A also points to the starting node of what? See, poly pointer A is pointing to the starting node of A polynomial, and I say start A is equal to A, even start A also starts pointing to the first node of the polynomial A. OP people understood?
Yes, sir.
Okay. Next, what I'm doing, A is equal to A arrow link. So I'm just making, see, since I've taken A, start A already pointing to the node to which A was already pointing. Now I go for making. Now what the statement will do, this statement will make A to point to the next node. So initially it was something like this. Say this is my A polynomial, and -1, this is my header node, and I have something here. So 3, so let me take the same thing, 14, and then I have one more thing, I don't remember what it is, 2, 8, 2, and this is 8, and there's a link to this, and next one is 1, 0. One, 0, and this is pointing here, and this is right now pointing to this, and A was already pointing to this. Getting? You understood this status? Yes or no?
Yes, sir.
Okay, now you observe. Now when I say start A is equal to A, even start A also start pointing to this. Start A is also pointing to this, but my actual polynomial terms are starting from here. Correct, right? Now what is that I'm doing? A is equal to A arrow link. A is right now pointing to this node. Now I don't want A to point to this node right now. I want A to point to this node. Okay, now what is that I have to do? I have to make A to travel from this node to this node. How to make? Because the address of this node is present here. Now I want to make A access this field. A is equal to A arrow right link. Sorry, link. A arrow link is this field. Okay. Now here there is an address, and that address, now what I'm doing, I'm assigning it to A. That means A, after this statement executes, A is not pointing to this, A is pointing to this. I made A poly pointer A to point to the first term of my polynomial. OP people understood?
Yes, sir.
And similarly, for the other polynomials, I have B polynomial. Please mute. Yeah, I have other polynomial also. Okay, so other polynomials also. Instead of start B, I'm not taking it. If you want, you can take start B also. So start B is equal to B, you can do it. So just similar to this, you make start B point to the header node of the second polynomial or B polynomial, and just make B to point to the first actual term of the B's polynomial. And after that, so what we are doing, say this is my first polynomial, and let me write the other polynomial also. Here you can write this also. If you're interested, you just write start B is equal to B. Okay, let me write the other polynomial here. Oh, sorry. Okay, let me write here. Don't look into this. This is my other polynomial B, and here also it is -1, and we have B already pointing to this, and then what I'll do now, let me take this example itself, the B polynomial. So it does 8, 14. Say B polynomial. I'm taking this polynomial B 14. Okay, so this is 8, 14, and this is pointing here. And what is the next one? Do you people remember? It is -3 and coefficient is -3. And what is the exponent? -3, and it is, I think, 10. And there's a link from here to here. And what is the last one? Do you remember? In the B's polynomial, what is the last term?
10 and 6.
10 and 6. 10 is exponent, huh? Yeah.
Yes.
So coefficient. 10
So
is
coefficient.
6 is exponent, and this is the link, and this is now pointing to the beginning again. Now when I say start B is equal to B, even you have start B pointing to this, start B is also pointing to this. Now I have to make B, but my actual term of my B polynomial is starting from the second node. I just say B is equal to B arrow link. So now B is no longer pointing to, once this statement gets executed, B is no longer pointing to this, B points to this node. Correct? Yes or no?
Yes, sir.
Okay, now you observe. Okay, D is equal to get node. See, this is my first polynomial, this is my second polynomial. Now I need to build a resultant polynomial. Okay, so resultant polynomial. Now what I'm doing, see, D is equal to get node. When I call this function, a node gets created. With 3 fields. Okay, so D, and D is pointing to this. Say, since I've told D is equal to get node, so node is created, and address of this node is returned to what? D. Now D is pointing to this. This is a pointer to my resultant polynomial, and what I'm doing, D arrow exponent. So this field again I'm making it as -1. Okay, and last is equal to D. Okay, see D is already pointing to this node. When I say last D is equal to D, so last D also points to this. Hope you people are following. I have one more pointer to this. What is it? Last D. D is also pointing and last D is also pointing. Now I go here, do switch compare A arrow exponent with B arrow exponent. What is A arrow? A is pointing to this, and A arrow exponent is how much? 14, and B arrow exponent is how much? 14. So I'm comparing. What compare will return now? See, 14 and 14, they are same. If they are same, what compare should return? What is the return value from compare?
3.
What compare returns if both the exponents are same? So please louder.
0.
0. It returns 0. Now switch to case 0. Okay, where it comes to case 0 here. Okay, now what you are checking here, if start A is equal to A, okay, done is equal to true. So I am checking whether I am done with all the terms of my polynomial A. Okay, so if start A, observe here, if start A is equal to A, now where is start A now? Start A is pointing to this node, and A is pointing to this node. Start A address is different and A address is different. They are not same. Correct, right? Yes or no? So when this A reaches last this node, and if I say A is equal to A arrow right link, A comes back and points to this node again. Okay, so then start A will be equal to what? A. Right now start A is pointing to this node and A is pointing to this node. That means we have not yet covered all the terms of the polynomial A. Okay, see here. So if start A is equal to A, that means what? You have done processing all the terms of the polynomial A. Make done is equal to true. Now this is not true now. So we come to the else part. Now what you got to do? Take the coefficient of A, take the coefficient of B, add them. What is the coefficient of A? 3. And what is the coefficient of B? 8. 3 plus 8, 11 it is. You are adding them. Okay. And then what you are doing, so 8 plus 3, 11 goes to sum. Now if sum, okay, so sum, if sum exists, okay, if sum, attach sum exponent and last D. Okay, observe. So you are calling the function attach sum exponent and last D. What this will do? Okay, sorry. So this will do, so the attach is going to create one more node is created, and 8 plus 3, 11 is assigned here, and exponent is how much? 14 comes here, and last D is not pointing to this now, so last D points to this. And there's a link established from here to here. Hope you understood? Hello?
Yes, sir.
Yeah, and who's doing all these things? This function is doing, attach function is doing. In attach, what we are doing, we're creating one more new node, and to that new node, as the exponent, sorry, coefficient field, I'm assigning sum, and for the exponent field, I'm assigning A arrow exponent, and I'm making last D to point to it. Okay, and after this, what we got to do? A is equal to A arrow link and B is equal to B arrow link. What happens? So A was point. I'm done with this and this node. So now A is incremented and point here. A is pointing to this, and similarly B is also incremented and made to point to this. Okay, next what you do? So while not done, you'll check. So done is still false. So while not of false is true, what happens? It comes to this again. Again compare A arrow exponent with B arrow exponent. So A arrow exponent is how much now? 8, and B arrow exponent is how much? 10. You're comparing 8 and 10. Now, since 8 is lesser than 10, so compare should return you -1. Case -1 it comes here, and then attach. What is that you are attaching? B's coefficient, B's exponent to last D. Okay. So now there is one more node gets created here. B's coefficient is -3 and its exponent is how much? 10, and there's a link, and this is not pointing to this, so it is pointing to this. Why we have taken the name as last D itself? Because it always points to the last term of your resultant polynomial D, hence it is called as last D. Okay, so the process continues, and finally what we do when you are done with all the terms, okay, you can just observe here. So last D arrow, see, when you finally finish all the terms, when you cover all the thing, so last D, you know, it is already pointing where? To the last node. But I have to make this resultant polynomial also as circular. So how to make this last D, correct? No, point. See here, last D arrow link is equal to D. See here, assume this itself is the last node, and last D is pointing to this, and here I need to store the address of the first node. How do I store? See, D is still pointing to this. D is still pointing to this, but last D is pointing to the last node. Now tell me the statement, how to store address of this node here. Hello? So I want to store address of this first node here. So only when I store address of this node here, so a link will be established from this to this. Now how to? What is the statement is? You got to answer me. Am I audible?
Yes, sir.
Yeah, so tell me that statement. How do I store address of this node here? It's easy, you can tell. See, this node, address I need to store here. And for this node, D is pointing to this node, and for this node, last D is pointing to this node. Now what is the line I need to write? So here in this field, observe my mouse movement. In this field, I need to store address of this field, this node. Now first I have to access this, correct, right? This field I have to access. How do I access this field? Tell me. Oh God. Now how to access this field? See, are you people following what I'm saying?
Last D arrow link.
Last D
Arrow link.
arrow link. That's it. See, when you know, please do respond back immediately, because you're not in front of me to understand with your expressions. Okay. So only when you respond back immediately or quickly, I can understand how you people are following. Okay. Now I can access this field. Okay. This field by writing last D arrow link. I'll write here last D arrow link is equal to, now what is that I have to store here? Address of this node, and to this node who is already pointing? D. Just write here last D arrow link is equal to D. So in this field, you're assigned to this field, you're assigning the address of this node. That means the link will be established from here to here. Understood? And the same thing is written here. So once you're done with all the terms, the next thing what you got to do is last D arrow link is equal to D, and then finally return D. Understood? So D is pointing to what? So D is pointing to the first node, and you get the resultant polynomial. Okay, people, understood?
Yes, sir.
How are you feeling? Are you people feeling it's difficult or easy? See, once you understand everything, it's easy. It's not at all difficult. Only thing is how to use the pointers appropriately and how to travel from one node to the another node, how to access the fields of the nodes. So all these things, if you are clear, then this is not at all a difficult. So you can do whatever you want using this singly linked list or doubly linked list. You can go for writing, solving your own problems using these concepts. Okay, so I think you understood how to do it, how to represent the polynomials using the circular list with header node, and how to perform the addition of two polynomials using the circular singly linked list. Okay, so next is, and similarly the other cases, if the coefficient of A is bigger than the coefficient of B, then what we do, we attach the coefficient of A and exponent of A and to last D. Okay, and then we go for incrementing only A and we make B stay there itself. So next is, okay, I forgot to write the heading, 1 second. Sparse matrix So sparse matrix representation using singly linked list. So you know already what is a sparse matrix. Okay. Now, how do we represent a sparse matrix using a singly linked list? Sparse matrix is the one which has more zero elements than compared to what non-zero elements. So very few non-zero elements you'll have, but you will have a larger number of zero elements. So that is called as a sparse matrix. So you understood how to represent the sparse matrix using what is the method that we understood in order to represent the sparse matrix earlier? What is that method called as? Triplet representation. Okay, so that was now the same, and I think I told that time there is one more way of representing the sparse matrix, that is linked representation of the sparse matrix. So that that point of time I didn't mention about linked representation because the concept of singly linked list, everything was required. And now you know the concept of singly linked list. Now it is time to understand how to represent the sparse matrix using the singly linked list. Okay, so now you just observe here. Okay, so I have written here a node. So this is how I represent the header node here, and then the element node is represented something like this. So you can have a look here. So header node, I have next. Okay, down and right. So there are basically three fields here. Okay, so this down points to the holds the address of the node which is just below, and right holds the address of the node which is towards the right, and next holds the address of the next node. So something like that. And then similarly the element node is represented like this. So we are representing the element node using 5 fields. Okay, one is row number, column number, its value, and then down. So this is a pointer which holds the address of what the node, the next node, which is down, and right obviously it holds the address of the node which is towards the right side. OP people understood with the representation of header node and element node in case of the sparse matrix representation using singly linked list.
Yes, sir.
Okay. See, initially when we started with the singly linked list, we started our discussion with a node having two fields. One is the info field and the link field. And then when we started discussing the application of singly linked list to the polynomial addition, so we expanded our understanding. So to represent a polynomial using a singly linked list, a node with two fields is not sufficient. Okay, I need a node with three fields, one for holding the coefficient, one for holding the exponent, and one for holding the link. And similarly, now when I go for representing the sparse matrix using the singly linked list, so three fields are sufficient for me to represent a header node, but three fields are not sufficient for me to represent the element node. So because when I say an element of a sparse matrix, it is determined by a row value, column value, and also its value, and again this element, if I take this element, say it is linked to two things. It is linked to this one and it is also linked to this one. Now to represent this node, I require a pointer which holds the address of this node, and I also require a pointer which holds the address of what the node which is just below it. Okay, so this is how. Now I found that to represent a node, element node, say distinguish, there are two things here, header node and element node. To represent an element node, how many fields are required? 5 fields are required. One is row, one of them is column, another one is value, down and right. Okay, and this is one example for the sparse matrix. So this is a sparse matrix. Why this is a sparse matrix? Because there are fewer number of non-zero values, so than compared to the zero values. Okay, if this is clear, so I can move on to the next slide. Any doubts in this?
No, sir.
Okay, observe now. So this is how the singly linked representation of the sparse matrix. So I am trying to represent this sparse matrix using the concept of singly linked list, and using this representation for the header node, and using this representation for the element node. Okay, have a look here. So these are the header nodes. What you're seeing here is these are the header nodes. This is one header node, this is another header node, header node, header node, header node. Now how many such header nodes are required? Okay, that depends on, see, let me write here. So okay, so number of header node, I'll write HN, number of header nodes is equal to max of okay, let me write here down, number of header nodes is equal to max of number of rows comma number of columns, COLS, close the flower bracket. Okay, so the number of header nodes required is computed by taking the maximum of number of rows and number of columns. How many rows are here? 1, 2, 3, 4, 5. So max of number of rows is 5. How many columns are there? 1, 2, 3, 4. Now what is the maximum of 5 comma 4? 5. So the number of header nodes required is how much? 5. You require 5 header nodes. I'll go here. Just have a look here. This is header node 0, header node 1, 2, 3, 4. 1. So this is starting from 0. 0 to 4 is nothing but what? 5. So this is first header node, second header node, third header node, fourth header node, and fifth header node. Okay, and similarly, so header nodes are represented. It's Paka representation of the matrix format. So header nodes are represented here also. See here. So this is header node, first header node, second header node, third header node, fourth header node, and fifth header node. OP people understood? So how do you decide the number of header nodes required? So it is by taking the maximum of row number of rows, and number of columns. So here in the example which I have taken, there are 5 rows. Okay, so hence I require the 5 header nodes. Is that clear?
Yes, sir.
And this header node which is at the corner, it is saying there are how many what is it, columns? 4 columns. How many rows? 5 rows. And how many non-zero values are there? 6. You can count here. Sorry, 1. This is one non-zero value. 1, 2, 3, 4, 5, 6. Okay, there are totally 6 non-zero values. So this header node which is seeing at the corner, it is showing you, so the same triplet representation, even the triplet representation, the first row we used to write it like this. Okay, so total number of columns, total number of rows, and total number of non-zero values. Okay, and apart from this corner header node, so I have 5 other header nodes and the row, and 5 other header nodes at the column, something like this. And I will look into this header node now. So this is the next field, this is the down field, and this is the right field. Clear now? Yes, or no? Yeah. Now see, since this is the next field here, just have a look here. This is the header node, this is the next field. Okay, what the next field is doing, observe here. The next field is holding the address of the next header node here, this header node, and this next field is holding the address of this node, and this next field in this header node is holding the address of this node, and this is holding the address of this node, and again, so this next field, so I made it to point to where? Back to this. It's something like a circular linked list. OP people understood, no?
Yes, sir.
Yeah. Next, just let me go here. See, I have a non-zero value 2 present here. This is what row? 0th row. And what column? 0th column. Okay, so it is at the 0th row and 0th column. Now this is an element node now. So sorry, yeah, let me this header nodes I've completed. Okay, next here, so this header node again. Okay, I'll come to this header node later. Let me take this element node. This is an element node now. Now I come here. So this is an element now, non-zero value. Now it is represented using this format: row number, column number, and its value. You can just observe here. Row number 0, column number 0, and what is its value? 2. Okay, next, and this is down and then right. Okay, so down points to the node which is just below, and right points to the node which is to the right. Observe here. So down is pointing to this. Okay, so this we haven't yet written. Okay, down should point to this. And next, in this row 0, there are no other non-zero values. Okay, so this is also 0, this is also 0, this is also 0. Now what we are doing, so we in this right field, right now we are storing the address of this header node, the header node which is here. OP people understood? And this header node is nothing but what? This node, H0. So don't think there are 10 header nodes, there are only 5 header nodes. So this field is pointing back to this node right now. So I cannot show here, no, it's very difficult, that's why it's written here. OP people understood? Or this field is holding address of what? H0. Clear?
Yes, sir.
Okay, next, I have next non-zero value in row 1, column 0. Now how do we represent it? See here, row 1, column 0. Okay, and then what is its value? 4. Okay, next, so down field. Okay, so again down, see there is one more non-zero value 8, which is at column 0, row 0, 1, 2, 3, row 3. Okay, so from down is pointing here, and the right, see on the same row, row 1, there is one more non-zero value. So one more non-zero value at column 0, 1, 2, 3, column 3. You can see here, it's pointing to this node. So this right field of this particular node is holding the address of this entire node. Okay, and then since this is the last non-zero value here, so the right field of this node is again pointing back to h2. So h2 is nothing but this node. This node it is pointing. So if I put a line from here to here, it looks odd, so I have written it here also. I'm just showing it like this. So now it looks something like an exact matrix. Correct, no?
Yes, sir.
Yeah. And then have a look into the third row. This one. There are no non-zero values in this row. There are no non-zero values. Now what we are doing, we are making the right field of this header node to point to itself. That means, so this field contains the address of its own node, and there are no non-zero values here. No non-zero values. Or in other words, this h2, this field, see this is, I have not pointed anywhere, and the same thing is shown here. So I can just write like this also. So it is holding its own address. Okay, and similarly, so in the next row 8, so 308, and as I already told, this node is pointing to this, and yeah, and again after this 8, there are no more non-zero values. So if I just look below, downwards, after 8 there are no more non-zero values. What should happen? So this down field should again, see, point back to this header node h0. See, down field, because I got to make it a circular. So down field is again pointing back to this h0, and since there is another non-zero value 1 in the same row, the right field of this node is pointing here to this node. Okay, so hope you people understood.
Yes, sir.
Okay, and observe this for h1 node, h1. So that is column 1. So this is column 0, and this is column 1. So column 1, there is no non-zero values. Now observe header 0, header 1 down field. Since there are no more non-zero values, so the down field of header 1 is holding address of itself. So this is how the sparse matrix is represented using the concept of singly linked list. Okay, so now what I'll do is, so take this as an example, okay, and try to represent using this circular linked list representation of give the circular singly linked list representation for this sparse matrix. So copy this. So all of you should do that now. So because 10 to 11 also I'll be continuing, because ADE class you don't have. So I want you to try this for some time. So I haven't had my breakfast yet. So let me finish my breakfast. So meantime, I want you people to represent this sparse matrix using a circular linked list. Can you people do it?
Yes, sir.
Yeah, just copy this. What I'll do, for your reference, I'll just keep this slide open. Okay, so just copy this problem statement. So this matrix, sparse matrix, you copy. Just tell me the moment you finished copying. Copied?
Done, sir. Yes.
Yeah. So this I'll just keep it open for you. Just try to represent it. See, if there is no non-zero values in a column, the down field of that particular header node should point back to itself. And if there is no non-zero values in a row, the right field of that particular header node should point to itself. Okay, so this thing is very important. So they'll ask you in exam also. They'll give a sparse matrix and they'll ask you to give the circular linked representation of the same. You should know how to do it. Okay, so keep doing. So all of you should do it, and you have to share the answers to me. So meantime, I'll just finish my breakfast and come back. So I'll stop recording. I'll just pause. Left out. Anybody has not checked your marks? Yeah, anybody there who has not checked it?
Excuse me, sir.
Yes, ma'am.
Sir, I have attended maths, but it's showing not attended.
No, it's not. No, I think it's still not evaluated.
Okay.
So sometimes, so they might have evaluated few answer script from your section, and yours is not yet evaluated. For all questions, you're getting it as NA?
Yes, sir.
Yeah, that means they have not started your evaluation yet. Okay, you can check all subject marks there. So any other subject still not evaluated? Only maths is not evaluated, huh?
Yes, sir.
Okay. Now this link, checking the marks, and even you can also view your attendance status. So these two things I'm just planning to include them in the college website. Okay, and you can access directly from there, and I think soon I'll be doing it within by the end of this week I'll be doing it, and you people can any point of time, not only my section students, all students of the entire BIT college can go to the website, college website, and you can open. I'm just planning to create something called a students corner there, students e-corner. You can just go there, and all of you will be given the login credentials also. You can use your login credentials, you can log in, and again, if it is second test, you got to log in. First test there was no login credentials given for you to upload your answer script. Now I'll be providing the login credentials for you. You have to log in and you got to upload. Okay, and you don't have to choose. What you need to choose is only the subject, for which subject you are uploading. So that subject you have to choose, and you have to upload your answer script. And say for example, today morning you have the test, say data structures and application. So now this time you can upload only the data structures and application. You cannot upload other subjects. Okay, and you cannot upload for the other students also, because login credentials will be given. So you can log in and you can upload only your answer script. Okay, that is what I have planned, and by this weekend, okay, so you'll soon see a tab in the BIT website with the students e-corner, and you can use that to view your marks, attendance status, everything. So I think so few of them have started marking attendance also using my portal, and but marks everyone is doing, entire college is doing.
Sir,
Yeah, finished.
sir, I was doing my mark
Yeah.
and I signed in. and after that it is again showing me in that page only review permission.
That
Click
means
on allow test.
try to do it again. It will open. You have to log in using your Gmail ID.
Sir, I have logged in and then clicked allowed even, and again it's showing review
No, it will
permission.
happen. No. It will happen. Try again.
Sir,
And those who have finished solving the problem which I gave can go for sharing.
Sir,
Yes.
sir, I have written part B 4A, sir, but the marks is not displaying, sir.
You just WhatsApp me, okay? Your USN in which
Okay.
subject? My subject, huh?
Yes, sir, your subject.
Okay, I'll look into that. Okay, WhatsApp your USN and the question number where you have doubt. Okay, I'll see the answer script again.
Okay, sir.
Okay. Yeah, don't waste time. Soon finish solving that problem and share it to me. So I have connected to the other meeting also. There is MTech presentation happening. So I'm supposed to be there. My student is presenting. I have to join it while she is presenting. Again, I may go on hold for some time for this meeting, and I may join the other one. Okay, and before that, if any of you have solved it, please share it. So I just want to have a look.
In saving our time, manual effort in testing regressions whenever there's a code deployment. So in a CI/CD structure, it will be helpful when we enable automation in between. So that's my problem statement. Next, talking about individual work or group work. I have worked with test case designing and execution, exploratory testing, functional testing, and regression testing. So initially, when I joined the team, I got an opportunity to run more than 1,000 test cases. So that in the beginning, it was more like an exploratory testing because we knew the major functionalities of the overall application. But then to get into details of it, we had to do an exploratory testing. So we've run more than 1,000 test cases in the beginning. I work for more than 3 sprints now. And talking about defect and feature identification, so every time we did a regression testing, we were able to identify defects and also suggest new features that could be added.
Excuse me,
Yes, sir.
Madam, Girija madam.
Oh.
Hello, madam. Mamta madam. ಹಲೋ ಮೇಡಮ್. ಮೇಡಮ್ ನನಗೆ ಐ ಹ್ಯಾವ್ ಕ್ಲಾಸ್. ಆ್ಯಕ್ಚುಲಿ ನಾನು ಅಲ್ಲೂ ಕನೆಕ್ಟ್ ಆಗಿದ್ದೀನಿ. ನನ್ನ ಸ್ಟೂಡೆಂಟನ್ನು ಯು ಕ್ಯಾನ್ ಕೀಪ್ ಇಟ್ ಅಟ್ ದಿ ಎಂಡ್ ಮೇಡಮ್. ನಾನು ಈ ಮೀಟಿಂಗಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಗಿರ್ತೀನಿ, ಬಟ್ ಮೇಡಮ್ ಅದೇ ಆನ್ ಹೋಲ್ಡಲ್ಲಿ ಇರ್ತೀನಿ ಮೇಡಮ್ ನಾನು. ಸೊ ಐಲ್ ಬಿ ಕನೆಕ್ಟಿಂಗ್ ಟು ದಿಸ್ ಮೀಟಿಂಗ್, ಬಟ್ ಆನ್ ಹೋಲ್ಡಲ್ಲಿ ಇರ್ತೀನಿ. ಅಲ್ಲಿ ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಕ್ಲಾಸ್ ಇದೆ ಮೇಡಮ್, ಮುಗಿಸ್ಕೊಂಡು ಇಲ್ಲಿ ಬರ್ತೀನಿ ಮೇಡಮ್. ನಂದು ಮೈ ಸ್ಟೂಡೆಂಟ್ಸ್ ಯು ಕ್ಯಾನ್ ಕೀಪ್ ಇಟ್ ಅಟ್ ದಿ ಎಂಡ್.
You just tell us.
ಹಲೋ ಮೇಡಮ್. ಹಾಂ, ಕೇಳಿಸ್ತಾ ಇದೆ ಮೇಡಮ್. ಹೇಳಿ. ಅಲ್ಲಿ ಕ್ಲಾಸ್ ಮುಗಿಸ್ಕೊಂಡು ಬರ್ತೀನಿ ಮೇಡಮ್ ನಾನು. ಅಂದರೆ ಇಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಗಿದ್ದೀನಿ ಆಲ್ರೆಡಿ, ಅವ್ ಕನೆಕ್ಟೆಡ್. ಆನ್ ಹೋಲ್ಡಲ್ಲಿ ಇರ್ತೇನೆ, ಬಟ್ ಅಲ್ಲಿ ಕ್ಲಾಸ್ ಮುಗಿಸ್ಕೊಂಡು ಇಲ್ಲಿ ಬಂದು ಜಾಯ್ನ್ ಆಗ್ತೀನಿ. ನನ್ನ ಸ್ಟೂಡೆಂಟ್ ಎಂಡಿಗೆ ಕೊಡಲಿ. ಓಕೆ ಮೇಡಮ್. ಥ್ಯಾಂಕ್ ಯು.
ಹೌದಾ? ಹಾಂ ಹೇಳಿ ಹರೀಶ್, ಏನು ವಾಯ್ಸ್ ಕಟ್.
ಅದೇ ಇವಾಗ ಮೇಡಮ್ ಕ್ಲಾಸ್ ಮುಗಿಸ್ಕೊಂಡು ಬರ್ತೀನಿ. ನನ್ನ ಸ್ಟೂಡೆಂಟ್ ಎಂಡಿಗೆ ಕೊಡಲಿ ಅಂತ. ನಿಮ್ದು ಇಬ್ಬರದು ಮುಗಿದ ಮೇಲೆ ಲೆಟರ್ ಗೀವ್. ಓಕೆ ಓಕೆ ಮೇಡಮ್ ಕೇಳಿಸ್ತಾ ಇದೆ ಥ್ಯಾಂಕ್ ಯು ಓಕೆ ಮೇಡಮ್
Can I continue, ma'am?
Sorry for disturbing you.
No problem, sir. I'll ping you, sir, then once I'm done.
Okay.
All right.
Yeah, Sonia, you can continue.
Okay, ma'am. All right. To continue,
Okay, when will the lab internals be conducted? So it's next week. In your respective labs we are conducting. So and my yesterday batch, I don't remember the batch number, it has finished executing till 6th program. Qs also they have completed, but it's not possible for the batch which has lab on Friday and Saturday to complete it, and even Monday was also holiday. So for that reason we have planned to keep till the 5th program. Okay, till 5th program we'll be having the lab internals next week in your respective labs.
Sir, will there be Viva also? Or just waiting?
Yes, Viva will also be there. We'll be asking you the Viva questions also. And sir, I've sent the answer through WhatsApp. Okay, I'll just check.